Hello guys. First and foremost, I will introduce to you how principles of chemical engineering is applied for our IDP. Material balance is the calculation of all materials that enter and leave any system or process based on the rule of conservation of mass. According to the equation, total mass flow rate of input stream is equal to the total mass flow rate of the output stream. For energy balance, it is known as the external energy that is processed by the products. According to the first rule of thermodynamics, the total energy of a closed system is equal to the sum of heat transferred from the surrounding to the system, Q, and the work done on the system by the surrounding, which is W. Now we will talk about the background of our product, which is acetic acid. Acetic acid is commonly known as ethanoic acid. It is a colorless, corrosive liquid that can cause skin irritation if it's highly concentrated, and it's frequently found in vinegar solutions. To ship acetic acid, it must be placed in a container that is clean, dry, and gently handled. Any alkali substance have to be kept away from acetic acid to prevent chemical reactions from happening. And it also poses a moderate fire risk when shipping. Next, the pump and the pipes that are used in these chemical plants have to maintain high pressure for a long period of time. All pumps and pipes must be leak-free to avoid any accidents from happening in the chemical plant. To calculate the pumping characteristics of acetic acid, we must assume that liquid is incompressible, it has a steady flow, and uses frictionless pipe. Before plugging in the values to the Bernoulli's equation to determine the inlet suction and pump discharge.
So hello, I'm Gabriel. I do the part for the chapter 2 Principles of Chemical Engineering. We have seen multiple reactions to produce acetic acid, and we chose the reaction from acetaldehyde to produce acetic acid. So this reaction needs O2 to work. The O2 can just be pure O2 or can be bring it in air, and the acetaldehyde will be in liquid form. So the reaction needs specific condition to occur, 150 degrees and 33 bar to work. So our reactor needs to respect this condition to make the reaction happening inside the reactor. Also, we use catalyst to speed the reaction. So we will use cobalt to make it quicker. The reaction yield of acetic acid is 95%. So the reaction creates the main product created is the acetic acid that we wanted, and the bioproduct is like acid formic and ethyl acetate. So after the reaction happens, we have to separate the different product and bioproduct. So to separate the different products, we will use distillation column. So acetic acid boils at 118 degrees Celsius, formic acid at 100.8 degrees Celsius, and ethyl acetate at 77.8 degrees Celsius. So we will use different distillation column with different temperature inside to separate the different product and bioproduct. So hello, basically we see the flow S1 is acetaldehyde and the flow S2 is O2 or air. They enter in the mixer, the mixer mix the liquid and the gas, and after it sends into the first reactor called Sept 4. The Sept 4 is heated by a furnace and to 150 degrees Celsius and at 33 bar. After the reaction occurs in the reactor, the rest of acetaldehyde goes by the top of the column and is cooled by C5, and the rest goes in the separator 1. The bottom stream of separator 1 S 8 is the catalysis, and the rest escape by the top of the separator and is excess. And it's basically all the products and bioproducts of the reaction, so acetic acid, formic acid, and ethyl acetate. After the H2 is the liquids to 77.8 degrees Celsius, it enters the distillation column called Sept, and the ethyl acetate turns into vapor and escapes the column by the top and is cooled by C4. The rest is liquid, so formic acid and acetic acid is liquid, and they go out of the bottom of the column. They are heated by H1 to 100.8 degrees Celsius, and it enters the second distillation column called Sept3. The acetic acid will remain liquid, so it escapes the column by the bottom of it, and is cooled down by C3. The rest is into vapor, so formic acid is into vapor, and it escapes the column by the top, and is cooled down by C2 to turns into liquid form.
The picture shown above is the piping layout of the system. The two valves in the feed controls the amount of oxygen gas and acetaldehyde fed in. The pumps shown under the distillation column 1, 3 and 4 ensures that the fluids reach their predestined places. The bent arrows indicate the 90-degree standard elbows, and there is a standard T present at the feed. For the piping of this acetic acid production plant, we have chosen 316 stainless steel pipes which have an inner diameter of 5 inches, density of 8000 kg per meter cube, and a surface roughness of 0.02 millimeters. There are 3 types of fitting used: one standard T, 8 45-degree standard elbows, and 8 90-degree standard elbows. A globe valve is used to control the stream of acetaldehyde entering into the system, whereas a relief valve is used to control the pressure of O2 gas entering the system. There are also a total of 3 pumps being used to force the solution upwards into 2 distillation tanks and the storage tank. Through the Darcy-Weisbach equation, we can determine the pressure drop in circular pipes. The equation is as follows: change in pressure equals to the friction coefficient multiplied by length over diameter multiplied by density over 2 multiplied by velocity squared. After detailed calculation, we have found out that pipe S3 has a pressure drop of 0.0476 kPa, pipe S5 has a pressure drop of 0.1110 kPa, pipe S6 has a pressure drop of 0.0313 kPa, pipe S11 has a pressure drop of 0.1140 kPa, and pipe S15 has a pressure drop of 0.1421 kPa.
Since force is needed to push the solution from a low pressure point to a higher pressure point, pumps are added into the system. All 3 pumps would have to exert different amounts of power, as each part of system either may carry fluids with different density or even have an entry at different heights. So, to calculate the power needed to pump the fluids, we can use the equation below, which is P equals to Q rho GH. P stands for power, Q stands for the volumetric flow rate, times with the density, times with the gravity, and times with the height. The power needed to pump the fluids based on the calculation by using the above method, by the above equation, which is P equals to Q rho GH. The power that needed for the distillation column 2 is 12.25 kilowatt. The power needed for distillation column 4 is 16.33 kilowatt, while the power needed for the storage tank to pump the fluid is 22.86 kilowatt. If we calculated the volumetric flow rate of the acetic acid using the equation which is Q equals to mass over density, where the mass is 1200 kg per hour and the density is 1050 kg per meter cube. We'll get a volumetric flow rate of 1.14 meter cube per hour, which means for every hour 1140 liters of acetic acid is being filled up, which means a huge size of storage tank is needed to store such amount of large liquid. Therefore, the suggested dimension of the storage tank would be in the height of 7 meters, the width of 15 meters, and the length of 20 meters.
After working on our IDP, we were able to relate this assignment with PCE and fluid mechanics to real-life situation that can be used in the future for our work life. At the same time, we were able to plan a good strategy between group members to develop the final product from start to finish. At the same time, we were able to learn about the many uses of acetic acid for different industries, and because of that, it made us appreciate chemical engineering more. That is all from us. Thank you for watching.